So in the last two lectures of this course, we will prove Urysohn's metrization theorem. So this theorem tells us that if we put certain conditions on a topological space X, then in the topology it actually comes from a metric, right? So first we begin with some preliminaries. So lemma, let X be a metric space. And define a function d prime. So we want to change the metric on X, right, as follows: by d prime of x comma y is equal to minimum of d of x comma y comma 1. Okay, so here d is the metric. Where d is the metric on X. Okay, so then d prime is a metric on X and induces the same topology as d. Okay, so let's prove this. So the check that d prime is a metric, so is a metric, is left as an exercise. Okay, so let's assume that d prime is a metric, and the open balls bd prime x comma r are the same bd x comma r. The open balls are the same when r is strictly less than 1, right? And since open balls of this type form a basis for the topology on X, this implies that both generate the same topology. So I mean, d prime is a metric, so it generates a topology, and d is a metric, so it generates a topology. So a basis for the topology generated by d is given by open balls of this type, and a basis for the topology generated by d prime is given by open balls of this type when r is strictly less than 1, right? So therefore both these are the same, and therefore the topology is the same. Are the same, right? So this proves, a lemma. Okay, so let us take the real line with the standard metric and we apply this construction to this and apply the above lemma. Right. So then we get that d prime x comma y defined to be minimum of the absolute value of x minus y comma 1 defines a metric on R which induces the standard topology. Okay. Now we will use this metric d prime, so we will use this to define a metric on Rn are indexed by natural numbers, right? So this is the countable product. So let me write it as xn, right, where each xn is equal to R with the standard topology, right? And this product has the product topology as always, right? Okay, so we define the following metric. So define d of x comma y. So for we take two vectors x and y in this Rn, and we define this d as supremum among all natural numbers d prime xn comma yn divided by n. Okay. So this supremum obviously exists because each of these d primes is less than or equal to 1, right? So yeah. Okay, so lemma. First we need to show that this actually defines a metric on Rn, right? The function d defines a metric on Rn. Okay, so proof. Clearly, this holds. This is the second condition for defining a metric. This obviously holds, just clear from the definition. And suppose if x is equal to y, then obviously the d of x comma y is 0, and conversely if this is 0, then this implies that the supremum d prime xn comma yn by n is equal to 0. So this implies that each of these is less than or equal to 0. Yeah, but that implies that d prime xn comma yn is equal to 0, which implies that xn is equal to yn. This implies xn. Right? So we are only left to prove the triangle inequality. So this condition also holds. Right? So let's prove the triangle inequality. So let we take 3 points. Right? So then we have d prime, since d prime is a metric, we have the usual triangle inequality, and which is divided by n. Right? So now using supremum of ai plus bi is less than or equal to supremum of ai plus supremum of bi. So using this relation we get, so when we take supremum over here we get d of x comma y is less than or equal to d of x comma z plus d of y comma z. Right? So this implies that D defines a metric. Okay. And the main theorem we will prove in this lecture is the following. This is the first step towards proving Urysohn's metrization theorem. So the metric D. So we have defined a metric on Rn. So this induces a topology. On the other hand, Rn also has the product topology, and the content of this theorem is that both these topologies are the same. Induces the product topology. On Rn. Okay. So let us prove this theorem. So let us first show that every open set in the product topology is open in the metric topology. Okay. So in order to do this, first consider sets of the following sets. So let we take any point in R space Rn, define this set to be those y in Rn such that psilon for j lying between 1 and k. Right. So it is easily checked that sets of this type form a basis for the product topology. On Rn. Right. So we will show that these sets are also open in the metric topology. Right. So let y be a point in this set. Right. So choose some delta positive and which is less than epsilon by k. Yeah. So that this ball around yj, this is a real number of delta, radius delta is contained the ball around xj of radius epsilon, right? So this should happen for j lying between 1 and k. So in other words, we have xj here, right? So for each coordinate j, this has length epsilon, and our yj is a point over here, right? For each coordinate, for each j lying between 1 and k, right? That's because y is over here. Okay, so choose a delta which lies between 0 and epsilon k. If you choose delta very small, then the delta neighborhood for all these yj's will completely lie inside this epsilon neighborhood of xj. Okay, so we claim that the ball in the metric topology of radius delta around y is completely contained inside this set. Okay, so let's check this claim. So suppose z is a point in this ball, right? So this implies that supremum, so this implies that d of, so let's first write d of y comma z is strictly less than delta, but d, recall this was the supremum over n d prime yn zn divided by n, right? So in particular, this implies that d prime yn zn by n is strictly less than delta for all n, and in particular also for j. For j lying between 1 and k, right? So this implies that d prime yj zj is strictly less than j times delta, which is less than or equal to k times delta, which is strictly less than epsilon for all j lying between 1 and k, right? And so this is the definition of this open set U. So let's look at this definition U, right? So this happens for Zj. So this implies that this ball d y comma delta is contained in U k epsilon, right? So we have this open set, we have this basic open set U x bar, or rather we have this set, yeah, U x bar k epsilon. We chose a point y bar over here, and there is an open neighborhood in the metric topology which contains this y, and it is completely contained inside the set. So we can cover this U x bar by open sets of this type, and that will show that this U x bar k epsilon is also open in the metric topology, right? So this implies that U x bar k epsilon is open in the metric topology. Okay. Now let us prove the converse. Yeah. So now, next we show that any basic open set BD x epsilon is open in the product topology. Right. So what we will do is, we will show that there is a set. So let me replace this by y. We will show that there is a set U x k delta such that U x k delta is contained in x comma epsilon. So let us try to see why it is sufficient to prove this claim. So let's start. So our aim is to show that this open set P D y epsilon, this set is open in the product topology, right? So we can do that if given any point x bar in the set, we can find a set U which is open in the product topology and completely contained inside this ball. If we can do that, then we can cover this. We can do that for every x in the set, and we can take the union of those, so that it will show that this B dy epsilon that's open in the product topology. Now, in order to show this, that given any point x, there is a open set in the product topology which is completely contained inside this ball. Note that for this x, there is an epsilon prime ball, right? This is BD x comma epsilon prime, right? Which is completely contained inside this larger set, and therefore we will show that there is a set of the type, this type U x bar k delta, which is contained in this smaller epsilon, this epsilon prime ball, right? So that will prove the assertion. So let's begin with the proof. Okay, so choose k such that, choose k large such that 1 upon k is strictly less than epsilon by 2, right? So then we claim that U x k epsilon by 2 is completely contained inside BD x bar comma epsilon. So let us prove this. So if Z is a point in this set epsilon by 2, then what this implies is that d prime xj comma zj is strictly less than epsilon by 2 for all j lying between 1 and k, right? So this implies that d prime xj comma zj by j is strictly less than 1 upon j epsilon by 2, which is less than or equal to epsilon by 2, right, for all j lying between 1 and k. Now on the other hand, if j is strictly greater than k, then d prime xj comma zj by j is less than or equal to 1 upon j, which is because d prime is bounded by 1, which is less than 1 upon k, which is strictly less than epsilon by 2, right. So therefore when we take supremum over j, d prime xj comma zj by j, this is equal to the distance of x bar from z bar. This is less than or equal to epsilon by 2, which is strictly less than epsilon, right. So this implies, so we started with this z and we showed that the distance of z from x in the metric topology is less than epsilon. So which implies that u x comma k comma epsilon by 2 is contained in P D x comma epsilon, right. So this proves that. So thus we have proved this claim over here. So we have proved this claim, right. So this proves that both the topologies, this proves that the metric topology and the product topology are equal. So this completes the proof of the theorem. So we will end this lecture here.